Good afternoon, everyone. This is a live session for the course, which is entitled as Introduction to Photonics, and this is the live session third. So we are going to discuss about the uh, this week, which is week three of the course content, and after that, followed by that, we will go for the few question answer sessions and doubt sessions also. I hope that my voice is clear to you. Can you please confirm, am I audible or not? Okay, so let's move towards the first brief description about the uh, this week's lecture. So we'll go step by step with the previous classes. Uh, Start from the week one, day one class. So the professor has already discussed all the informations, all the studies about the electromagnetic waves, uh, electromagnetic wave nature of light in detail, in depth. Also, he has given so many examples of the phenomena using the application also, and has been demonstrated multiple applications using this concept. So here we are going to discuss a little brief intro about the electromagnetic wave to quantum particles. So basically, we have already learned about the ray nature of light in the week one, and where we discuss about the refraction, reflection, all the phenomena, even the applications. After that, we have gone to the wave nature of light, after ray nature, followed by wave nature, and then week two, and we have discussed in-depth discussion about the diffraction, interference, and so many concepts, including the applications of each phenomena. Now we are going to discuss about the electromagnetic wave nature of the light, and for that we have to go for the fundamental rules of the propagation. As we know that the light electromagnetic radiations were established by the Maxwell's equation, where there are four equations he has derived. One is the Coulomb's law, second is Gauss' law, then Faraday's law, and Ampere's law. That you have to go through the in-depth discussion that you need to understand in depth to understand the electromagnetic radiation. Then there were discussion about the wave equation. I think I'm audible. Yeah, I have to. So in the wave equation, the del square E plus k square E is equal to 0. Similarly, it is also uh, uh, applicable for the H. Del square E, del square H plus k square H is equal to 0. So both electric field and magnetic field both becomes in this equation if you're putting it will be 0. So this is the typical graphical illustration of the phase and the electromagnetic wave radiations, where the amplitude or phase are shown here, and this is E, this is the magnetic field H, and the spatial temporal coherence also has been mentioned here, and this is the XY plane propagation direction is Z. So this is a typical electromagnetic radiation graphical illustration. Now we are going to discuss about the modes, optical modes, because we have discussed about the electromagnetic wave nature or electromagnetic wave nature of the light. So we have to understand why it is came beyond the wave nature of the light. So usually the wave nature of light tells us about the diffraction, interference, all these things. So the wave meets here. What is happening? The wave front interference and the birth of mode happens with the when it is we are considering as a wave nature of light and then electromagnetic radiation uh, wave nature of the light. So as you can see here, screen. As you can see here that the wave meets boundary. At the boundary, it will be having the incident and reflected field configuration overlap. Yeah. So we were discussing incident and the reflected field in configuration overlaps happens, and because of that, so many modes uh, generates because of the constructive and destructive interference, which are surviving. That will be a constructive interference, and which are diminishing or because of the violates the boundary condition, it will be destructive interference happens. And only specific angle yielding perfect round trip constructive interference survives. And those are eigen modes. And that's what has been discussed in the first lecture of the week 3 by Professor. And we are discussing these things here. Now we are going to discuss about the numerical aperture. What is the total, why it is very important, and how the waveguide works, how the coupling happens, and other things. To understand the guiding the light through the total interreflection, first thing is the coupling thing. That should be coupled properly. The light should be coupled properly. So to achieve the high optical propagation through the core and the optical waveguide, and also the efficiency of the waveguide. So the condition depends on the first thing is the total interreflection. For that, the acceptance angle, the the uh, laser acceptance angle should be greater than the coupling angle, critical angle. So the critical angle is defined as this one. Theta c is equal to sine inverse n2 by n1, where n2 is the Cladding's numerical aperture and n1 is the coarse numerical aperture. Sorry, new refractive index. I'm sorry for that. So this is Cladding's numerical refractive index, and coarse one is n1. This is the coarse refractive index. So we were discussing about the numerical aperture. Uh, so it's nothing but a uh, Na is equal to n sine theta. N is the refractive index. Here we are considering as a coarse refractive index, which is n1. So n1 sine theta. That is the numerical aperture. We can get this cone theta value here in this area. If I point here the pen, maybe. So this theta is the acceptance cone, and this up to this. Sorry. So this and this angle, between these angles, you can couple the light efficiently to into the waveguide or fiber optics. So here it's already written everything. An optical fiber is a dielectric cylindrical waveguide. We are considering a dielectric cylindrical waveguide. Also, it can be considered for the microwave. Maybe it will be rectangular metallic waveguide and different phenomena with the different electromagnetic radiations. We are discussing about here IR, NIR, and the visible region. So the optical fiber which we are using for the telecommunication purpose, which has been shown here. So the light is trapped within the denser core medium through total internal refraction. However, as an electromagnetic wave, this confines light form distinct spatial pattern known as second. Yeah. So known as LP, linearly polarized modes. So we have already discussed about uh, the total internal reflections and also understood that how the cone acceptance cone works based on the numerical aperture. What is the numerical aperture? Numerical aperture is nothing but the n n1 sine theta, or you can say that under root of n1 square minus n2 square sin theta, n1 square minus n2 square. That's it. So you can see here that the V number we need to consider about the optical modes. We are discussing your linear polarized mode. So if you are considering uh, uh, the fiber which can be uh, generate the optical modes, single modes or LP modes, linear polarized modes. So how it will generate the single mode and when it will generate the multimode. So if you consider this V, V is a V number. V number so says that the equation says that the P is equal to 2 pi A. A is the diameter of the radius of the core and divided by lambda, and this is the numerical aperture value. So this defines that whether the fiber is single mode for that particular wavelength or a multimode for the particular wavelength. So based on the wavelength also it depends. So if you are increasing the wavelength, it can become a the VE number will decrease. So it depends on this lambda also. And numerical aperture, obviously. Increasing the numerical aperture increases the V number. And increasing the core uh, radius also increases the let me erase this here. So you can see here this one. So all three variables defines the V number. Here we are considering that the V number is lesser than 2.405, which means the fiber is single mode fiber, and we are getting only the LP01 mode output at the when the light is propagating through the uh, through the optical fiber at the end of the fiber. So the only fundamental mode propagates whatever is coupled into the fiber, and the core diameter is close to the scale of the wavelength. So the d is approximately scale to the lambda here. And if you are considering the uh, multimode, so there will be two different. There are a number of linear polarization. So one of them is the LP11. What happens in this? The when the V number is greater than uh, 2.405, it acts as a multimode optical fiber or waveguide. So it will be having two maxima and center is nothing. So this side also you'll get some intensity, Gaussian beam, and this side also. So this is the LP11 uh, optical mode, or you can say that this is we are saying this eigen modes, linear polarized modes. Then if you're considering the LP21, so it will look like this way. You can see in the 3D visualization itself, one lobe is here, another is here. This, so there are four uh, uh, points where this LP21 gives the constructive uh, outputs, and those outputs are in the separated like this. This is your center. So that's why it is LP21 we are seeing. Okay. So moving to so the multi-field, sorry. So the multi-field configuration overlaps the propagation simultaneously, and the core diameter is vastly larger than the wavelength. So the D is larger than the wavelength. So it happens when the D is quite larger than the wavelength. Now we have discussed about the numerical aperture, accepting cone, and then optical modes which are coming because of the UV number also we have discussed how it is happening inside. But how we need to couple the focused light, or how we can couple the source light to the fiber. So for that, this is the fundamental schematic diagram where the plane waves, incoming waves from the laser is passing through the lens. Lens is making this uh, plane waves in the little curvy waves, and once it is reaching here, it will become straight plane waves, smaller plane waves at the tip, where the beam diameter, this is already focused here. So the focused beam diameter should be exactly, it should be similar to the core's diameter. If it is lesser or more, it will be having problem. Either if you are taking larger diameter, the beam diameter, if it is quite big, suppose this much big beam diameter is coming from the lens, it will not couple directly into the fiber, and it will also propagate into cladding. So the optical loss will be quite high. Similarly, similarly, if it is very tiny, then also it will make some problem. It will not couple into the fiber optics uh, with a highly efficient way, as when the diameter of both are matching each other, it will be very high coupling efficiency. So here it is mentioned that the source, the laser emits a macroscopic planar wavefront millimeter scale, because we already know that the laser is having the spatial and temporal coherence. Almost we can say spatial coherence, temporal, uh, uh, a monochromatic source means it will be temporal as well. So the lens phase front curve, the overcome diffraction limit, condensing the light into the minimum waist diameter, and then the match. The focus spot size must perfectly match to the fiber's fundamental mode space. Mode shape. The perfect overlap integral is required to couple into the fiber. So these are the things we need to understand. Already you need to go through the lecture, so you'll understand the equations, all the formulas, what is happening here. Then, if you are talking about the quantization of the uh, uh, light into packet, so uh, from continuous wave, we already discussed about the Maxwell's equation, the wave nature of light and other things, where light is fundamentally understood as a smooth, continuous electromagnetic wave, filing space without interruption or interruptions. Uh, now we are talking about the Max Planck. Max Planck has given the black body radiation. He solved the problem with that for that in 1900, and proposed that the atom emits light is quantized packet when electron drops energy level. So we already know this thing that Maxwell has given the quantized word, quanta word. Then Albert Einstein also deeply studied this one, and he gave the exact energy of the each quanta, which is E is equal to h nu. And based on that, we understood that the quantization is there in the light, and those things were uh, taken into the picture where for the diffraction again. So when the interference is happening or diffraction is happening, the double slit experiment was demonstrated again with the same wave and particle nature duality, and dual nature of light. So the single photon source monochromatic light is propagating. It will be act as a particle and wave nature simultaneously. And that's why we are getting this kind of spots, which is fulfilling the constructive and destructive patterns. You can see this is the border for the constructive and destructive interference. So here photons are heating, and because of that, this Gaussian kind of beams we are getting here in this reason, and where there is no photons are hitting, or almost negligible photons are hitting, there will be a destructive interference. So they have uh, uh, given the uh, duality of light. So light is emitted and ultimately detected on a screen as a discrete localized point of energy or a photon, and then wave a photon path of propagation through space is guided by an extending non-localized electromagnetic waves and the collapse. If the detector interrupts the photon mid-flight to observe its specific path, the wave function collapses and the interference pattern instantly vanishes. So to understand this, you need to go to the video. There is one YouTube video shown that shows how was this is fundamentally demonstrated using this dual nature of the light. Then, if you are considering um, the momentum and the energy and probability of the lights, if you want to know based on the quantization. So the light has the zero rest mass and has a tangible momentum. So the energy, as we know that E is equal to h mu, so it is also considered as c by lambda. And then the energy is inversely proportional to the wavelength. So 100 nanometer UV photon carries vast destruction energy, while 10 millimeter radio photons carries very little energy. While discussing about the momentum is becoming as a h by lambda, h cut by lambda. Let's just see, h by lambda actually. So it will become h cut k, and k is here. H cut is here, h by 2 pi. So okay. So this is how the momentum of the photons will be uh, calculated. So the photons possess absolutely zero rest mass, yet they carry real momentum. They can exert physical radiation pressure on a macroscopic object. So that is also known that very high beam energy, if it is interacting with very light, like a paper kind of things, it will move but the object. So that is also known that pressure creates on the object. Then the probability. So the classical intensity and the quantum probability is almost similar. So the brightest peak of the classical Gaussian uh, laser beam is simply the spatial coordinate with the highest mathematical probability of finding a photon. So the probability also we can consider as an intensity. So the PR at the defined area is directly proportional to the IR of that area. So wherever the intensity is very high in this place, the probability of the finding photons are very high. Here in this area, it will be very less, less probability. Here, very high probability. Now, moving towards the uncertainty principle, because we have discussed about we already know about the electrons uncertainty principle. Uncertainty principle is discussed for the electron, and for the photon also same thing happens. Same principle lies, which is Heisenberg's echo, which is photon uncertainty we are saying. So the energy del E and the del T time is greater or equal to h cut by 2. So this is already known for the electron that uh, the probability of the finding electrons and the uh, that uncertainty principle. Based on that, this is also known. So why this law and how it works? So to understand that the law, the uncertainty principle is a photon's energy frequency multiplied by the uncertainty of uh, um, the exact. Actually, here it will be mu instead of energy. So it will be understand easily. So the exact arrival time must always greater than the or equal to the Planck's constant, uh, which is divided by 4 pi. So if you are seeing the reality in reality, suppose you have very a perfect monochromatic light source, laser, which is having almost a full width half maxima in the few nanometer region. Or so, what will happen? The uncertainty of the frequency will become zero, almost zero. So del nu will not be you can't understand that the you can understand easily that the monochromatic light source will having the del nu is equal to zero. But what about the time? Time will become automatically infinity. So it says that the a perfectly monochromatic light source is physically impossible as it would require an infinite observation time. So it automatically the time uh, based on the time this will become infinite. So that's why this uncertainty certainty always there. So all particle light contains a degree of temporal randomness. So even you are taking a perfect monochromatic light, which is having the perfect frequency, will be having uh, del T infinite. And if you have a polychromatic light, you'll be having so many n number of frequency. So automatically the del T, if you have zero, but in the end you will be having the del nu infinite because already it's a polychromatic. Okay, so this is how the photon's uncertainty has been explained, can be explained, and then moving towards the powering the laser, a threshold device. As we know that the light, the any semiconductor, initially it requires huge power to generate the lasing action and population inversion, and then it will be having the threshold current, and suddenly the population inversion happens, and then that's why the coherent light propagate releases by the cavity, and that is called the lasing action. So the non-linear reality is the laser do not scale linearly from the zero. So initially it will be spontaneous emission, and suddenly it will be spike as a like a non-linear phenomenon. And we adjust potentiometer resistance to push the bias through the laser diode. So this is to align the laser and other things because this is already the um, for the experimental part where they want to do the focusing the laser and to show that to see that laser this area you can't see the beam spot because it will be too bright. So the spontaneous emission time, you can see the focused laser to couple the light into fiber, as you can see here. So when it is going to the stimulated emission, you can't see the beam spot, beam diameter by eyes. So initially you can keep at a low current, and after that you can see the spontaneous emission diameter, which can be focused again and defocus again. So to adjust the beam spot, and then you can increase the current, so it will give the lasing action. Then below threshold, the device acts as a LED emitting only weak random spontaneous emission. Above threshold, the device fundamentally alters state, achieving intense coherent stimulated emission. So anytime if you are trying to focus the light, so initially you should be in the spontaneous emission region where you can focus the light. After that, you can increase the light to the in the inversion, population inversion side. Now, as they have in the lecture, they have demonstrated the lab demonstration and the industry use for the same fiber, which is the telecom fiber used for the 1550 nanometer telecom wavelength. So as you can see that the fiber, uh, it's very difficult. It's not too difficult to understand that it can be a multi-mode fiber for one particular wavelength, and for another wavelength it can be a single mode fiber. So suppose you are buying a single mode fiber for the 1550 nanometer telecom wavelength. It can be used for the 650 nanometer or even for 1064 nanometer wavelength. It can be a multi-mode fiber for that. So how it depends, how we can say that uh, uh, based on the wavelength, how we can define that what could be the V number and how it will behave in the linear polarized modes. So the V number for this 1.92, this is the industrial use. They will mention that 1550 nanometer telecom wavelength one, and this is useful for the V number 1.92, which is below than 2.405. So it means that this is single mode fiber for the 1550 nanometer. But if you are considering the same thing, V number will increase to 4.4 for the same fiber if you are using the wavelength of 650 nanometer red laser. So here what will happen, there will be n number of uh, not n number actually. We can say that a few modes will be increased there. LP11, LP21, LP02. Those modes will be also incorporated in this automatically because of this is now this is working as a multi-mode fiber. So the single mode is not an inherent static physical property of the fiber cable. It is a wavelength dependent mathematical relationship. So we have already discussed so many things previously that in the till now that how to couple, what is the numerical aperture, what is the acceptance cone, and what are the reason behind the modes generation inside the fiber. And also we have discussed about the uncertainty of the photons, momentum, energy, probability, then the dual nature of the light. And based on that, if you see the demonstration here, so the single mode fiber, now we are going to the application part. So single mode fiber is not true for the all the wavelengths. And when it is, suppose it is injected in the shorter wavelength, red laser, standard time telecommunication fiber behaves completely different, acting as a few mode fiber or multi-mode fiber. So it depends on the wavelength and depends on the pore diameter, also the V number. So all are related to each other. I hope that you have already gone through the question. I can also show you what is the equation for this V number, relation between the V number and uh, let me check. So V number can be easily derived or can be understand what will be the V number. 2 pi r. R is the radius of the core of the fiber, lambda wavelength, and numerical aperture. So if you are keeping all these things values, you'll easily get the V number. And based on that, if you're keeping lambda here 650, automatically it will become the 4.44. And for the same core diameter, core radius or core diameter. So uh, the we have already discussed about the accepting cone, capturing the cone, numerical aperture. Here they have demonstrated the uh, real life how it is um, captured the light. So for that, the measurement by sweeping the photo detector, this is the photo detector, the output light that side we have already coupled the light. The light is coming from the fiber, and here it is making a cone output. To understand this, what could be the numerical aperture of the fiber? Or you want to measure the numerical aperture, you just couple the light and you can rotate this photodiode to this angle here to here. So what will happen? You will see the intensity up to here and here, and you will get some kind of Gaussian plot like this. So you will get 1 by E square somewhere here. That will be your uh, uh, the MFT, and below that 5% if you are considering this one, it will be your numerical aperture. Okay, so and that's how you can calculate the numerical aperture. I think here one more thing is I forgot to mention this, and now we are considering for this, so it means that we are considering here the new refractive index of air. So it's almost one, approximately one we are considering. So that's why the numerical aperture became here sine theta. So we need to we can calculate the theta, can put here, and based on that we can get the numerical aperture. So maximum numerical aperture, how much it could be? It will be like theta is equal to 90 degree, then it will be one. But it's impractical because there will be a critical angle theta c. So anytime there will be theta c, the accepting cone angle will be greater than theta c. Okay. So we have understood the complete architecture about the light, the theory. Uh, we we can we can understand through the theory. We already understood the Maxwell equation and electromagnetic wave, amplitude, phase, those things. Then applied engineering, we already applied on the optical fiber. We got to know about the V number and internal refraction. Then the micro quantum level, that photon, probability, and then quantization of energy and uncertainty. Then the linear polarized mode. All this comes into the this micro level quantum uh, uh, quantum nature of light. So to master the photonics to the to a fluidly transition between the three paradigms, calculating light is an electromagnetic wave, constraining it as an engineer and observing its fundamental probability as a quantum particle. So that's why we have already understood that light is not only the wave or not only the ray or wave, that's a electromagnetic radiation, including the particle nature also. So the duality. So in the advanced next lecture, we'll get more into the particle nature. We'll understand what is happening inside the during the due to the particle nature and those things. So till now we have understood this weekly lecture. I have not gone through all the equations. I hope that you have already gone through the lectures and you understood the equations, how we are moving through the V number to modes and modes to uh, the, the coupling, and how we can calculate the numerical aperture, how we can calculate the um, accepting angle, those things, even the mode numbers, how it behaves. Okay, so till now we have understood these things. If you have any doubts, you can ask me. Anything you want to discuss, just let me know. I hope that you understood all the things. You can type also if you are not comfortable with the voice. Please tell me if it is understandable or not. Sure. Okay. So, any doubts, or we can move towards the question answer session. If you have a little doubt also, you can ask me. I'm here to solve your doubts. Don't be hesitated. Okay, so let's move towards the question answer session. Uh, Here we will discuss each and every question. You need to give the answer first, if you are understanding. After that, I will explain if it is correct, or if it is correct, then it's well and good, and if it is not, then I can explain you after that. So the first question here is the in the context of electromagnetic optics, what physical condition determines the transition from a linear polarization to a circular polarization for a plane wave propagating in the plus z direction? Option A is mentioned is the components Ex and Ey must have a phase differences of phi is equal to plus minus pi by 2 or equal amplitude. And second, B, the phase differences phi must be an integer multiple of c of pi. And the option C, the wave must propagate through the isotropic medium with n1 is equal to n2. And the option D, components Ex and Ey must be perfectly in the phase with phi is equal to 0. Could you answer, please? Okay. Please answer. Try to answer this. Please confirm is it visible or not. Question is visible or not. What's the problem in the question? Is it zoomed or blurry or something? Okay, visible. So can you please answer this question? Already have uh, told this. Okay, so the correct answer here is the 5. 5 is equal to plus minus half 5 by 2. So this is the correct answer here. Why is it? Because for the linear polarization to circular polarization of a plane wave propagating to the z direction, so we already know that the linear polarization has the phi is equal to 0, and the circular polarization has the exact plus minus pi by 2. And elliptical, it will be having any side, E and Y in that plane. So we can define that one exactly. Based on the electricity, we can define that. So the circular polarized has the phase difference has of plus minus pi by 2 and equal amplitude. So that's why the the correct answer is option A. The phase difference must be integer or multiple. This is not possible. And the wave must propagate through the isotropic medium with n1 is equal to n2. We have already we are not discussing about the medium here. It can be propagate in any medium. Only the thing is like the light velocity will change, not the phase. It will not differ much in the phase. Then the D, the component Ex and Ey must be perfectly in phase with phi is equal to 0. This is condition for the linear polarization. Moving towards the next question. I hope you understood this question. Moving towards the next question. According to the wave picture of the dielectric waveguide, why are only specific eigenmodes allowed to propagate? Option A, the total internal reflection must occur at an angle exactly equal to the critical angle theta c. Option B, the electromagnetic field must satisfy Maxwell's equation and maintain constructive interference over a round trip. Option C, the refractive index N1 must be at least twice the value of the N2. Option D, the wavelength diameter D must be exactly equal to the wavelength lambda. Could you explain this? What could be the answer here? I hope the question is visible to you. You can just use your no. Okay, option A. Anything else? So you're saying the total internal reflection must occur at an angle exactly equal to the critical angle theta c. We have not discussed like this the eigenmodes. As if you remember the eigenmode uh, discussion here, you can see that the this is not only the condition that theta c should be there. At theta c only it will be the condition is that the V number of the fiber. So, and along with that, the another thing is that the boundary condition, the wavefront interference and the birth of the modes. So any wave which is propagating in the direction it will be having two uh, uh, fraction of the uh, uh, what we can say velocity. So one is propagating this direction and another is this direction. This is okay because this is propagating in this direction. But what about this one? So here what is happening? This one and this one when is it propagating? When the ray is propagating this direction, so it will be having again this phenomenon. So this one and this one will be having some interference, this mode, and because this velocity condition. So where what is happening, the interference happens. It is propagating this way, this way. So this and this, because of these two interference, this one and this one, there will be a constructive and destructive interference. And based on that, you can see here that the constructive interference is more brighter and survives, while the destructive interference doesn't survive. So this happens because of the Maxwell. This happens because of the electromagnetic field must satisfy Maxwell's equation and maintain the constructive interference over the round trip. So we are talking about this total internal reflection. So each and every uh, surface or the what we are saying here. Yeah. So this here you can see the only specific angle yielding a perfect round trip constructive interference survives. Those are eigenmodes. As we already discussed about this one. So it should be having the meet the boundary condition first of all. Then it should be reflected and reflected incident and reflected field configuration overlaps, and then the yielding of the round trip constructive interference. So this is very necessary thing, and that's how the eigenmodes allow to propagate. So this is the correct answer for this, not this one. This is just a phenomena of total internal reflection and the critical angle, the accepting cone angle, which is required to accept the light in that range region up to theta c. Okay. I hope you understood. Yeah. The B option B. Correct. What about this question? Please try to give answer. For a planar waveguide of thickness D and refractive index N1, which simplified expression approximate the condition of the mode to exist, neglecting phase change at boundary. What could be the uh, answer for this condition? Could you please answer? Just try to give answer. What could be the answer for this? Correct answer of this is option C. Why is it so? So, so the cos theta n for the planar wave thickness with the formula which is derived from the kx into 2d is equal to 2 pi n. And if you are considering this kx and other values you are keeping, then we will get cos theta m kx. This is k cos theta m 2d is equal to 2 pi n. And if you keep k value, which is 2 pi by lambda, so after keeping this will be the correct answer. Correct. Here 2 pi by lambda into n 2d cos theta. So this will be the correct answer for this. So now question, what is the physical significance of the V number? V is equal to 2.405 for a step index optical fiber. Could you answer this question? Option B, C, option C, not option B. Please answer, try to answer this question, son. Option A. Yeah, you're correct. So here the correct option is option A. So why it is correct? Because it represents the single mode cutoff condition where the below which only the fundamental LP 01 mode propagates. So we already discussed about these things. Then only the thing chart I didn't mention. Let me check that. Yeah, here. So if you are considering this N effective and normalized frequency, so you'll be having this kind of first propagation constant B. The uh, first mode will be there. There is zero. You're saying this one as first zero of zeroth order Basel function. Okay, so after that, where it is 2.405, what happens? It will start another mode, which is here it is LP01. Here it will be LP11. So initially it will be like this. Then another mode also start coming with that. It will be two modes will be there. This is the central area. So there will be a cutoff for the single mode below this. So anything below 2.405, it will be a single mode propagation will be there. LP01 mode. Nice. You're giving answer at least correct. Now moving towards the next question. A fiber has a cutoff wavelength lambda c is equal to 1200 nanometer. How does it behave? How does its behavior change when used with a 650 nanometer laser source? So could you try to answer this one? We are discussing with the cutoff wavelength. So the V number will be for this, it will be exactly, can I understand that what could be? Let's try to answer. Option D. Yeah, you are correct. Why option D? Because we are taking the cutoff wavelength of the fiber, which is lambda c is equal to 1200. It means that the V number, as we mentioned previously, that V number will be what? Uh, Inversely proportional to lambda. Let me see that. 1 by lambda. So if lambda is decreasing, so V number will increase. So we can say that in 1200, then V number will be 2.405. When this is 650, then it will be for the 1200. And if it is 650, then it will be obviously it will be higher. So based on that, we can say that this will become a fiber becomes multi-mode because the lower wavelength increases the V number beyond uh, beyond 2.405. So that can be also calculated for the uh, V point 650, sorry, 650 meter will be, let me write properly, V 650 is equal to V 1.2 micrometer, 1200 nanometer, we can write like 1.2 micrometer, divide by your, this is the cutoff wavelength, so your V number will be 2.405 and you need to multiply here with, I'll write here, you need to multiply this value with 1.2 into 10 to the power minus 6 and zero point 0.6 into 10 to the power minus 6. This will become 2, will be cancelled, then did I miss something? Yeah, so it will become V65. I think something I missed here. Okay, let me see this one. What mistake I have done here. So it will be higher than this value. I'll calculate and I'll come back to this question. Uh, yeah, I did some mistake here in this place. This was the V 1200 is 2.405 because this is cut off wavelength, no? So this will be 405 and multiplied by 1.2 into 10 to the power minus 6 and divided by 0.65 actually. This is 0.650 now, so 0.65 we can write. And after that calculating this, the value will come 4.44. Okay, so just this is the ratio actually. V65 650 divided by V 1200 is equal to, these are the wavelengths you can keep, multiplied by the V number of this. Now the next question. I hope that you understood this why it is happening, becoming multi-mode fiber. Then the next question is in the LPMN notation with linearly polarized mode in a fiber, what does the integer n represents? Could you please answer this? The ratio between the pore radius and the cladding thickness, the number of the intensity maxima in the radial direction, the number of photons allowed to the in that specific energy state, number of intensity maxima in the azimuthal phi direction. Please answer this D. Option B, radial direction. What about the M then? So our direction means radial direction. It's correct. So N represents to the number of intensity maxima in the radial direction, and M represents to the number of intensity maxima in the azimuthal direction. That is correct. So we it is asking if this one. So this is not correct. This is the correct. Other things are not at all correct. Okay. So the linear polarized mode M and N is given for the phi direction maximum intensity and R direction maximum intensity. Yeah, you are correct. Next question. When coupling a Gaussian laser beam into a single mode fiber, why is placing the fiber tip exactly at the lens focus critical? Could you answer it? Option A, at the focus, the wave front is planar, matching the plane wave like phase front of the fiber's fundamental mode. Option B, the lens focus is the only point where the beam diameter is exactly zero. It prevents the option C, it prevents the photoelectric effect from damaging the fiber core. And option D, the intensity at the focus is infinite, ensuring maximum energy transfer. Option wave, option A. So this option you're saying the focus the wavefront is planar, matching the plane wave like a face front of the fiber fundamental mode. Yeah, you're correct. We already have discussed this one phenomena. You can go there and check. As you can see here, the plane polarized light coming from the laser hits to the lens to focus the light. It makes the curved waves. It's not a plane waves. So once it is trying to focus at one place here, this place, so automatically from that, so automatically it will become planar here. Then again it will start becoming wave kind of thing, the curved one. So this place where the waves are there, that will be useful to couple into the waveguide. So that's what the question asked here. In question they asked is at the focus, the wavefront is planar, matching the plane wave-like phase front of the fiber fundamental. Okay, so correct. Moving towards the next question, what is the Rayleigh range Z naught in the Gaussian loop propagation? Option A, the maximum distance a ray can travel in a fiber before it suffers total interreflection. Option B, the total length of the fiber over which temporal coherence is maintained. Option C, the distance from the focus over which the beam maintains a near planar wavefront and the intensity is at least half of its peak value. Option D, the wavelength at which a fiber transition from being a conductor to a dielectric. What could be the answer for this, your Rayleigh range? Option C. Option C, the distance from the focus over which the beam maintains a near planar wavefront and the intensity is at least half of its value. Yeah, you are correct. So the Rayleigh range, what it defines is the depth of the focus where the beam uh, remains collimated. That is the collimated beam means it will not be diverging or converging. So it will be having the planar wave up to it will be having the planar waves, collimated wave. Okay, so the wavefront curvature is minimal. So this wavefront will be not curved. It will be linear, plane wave. Okay, so correct answer. Uh, Now, next question. According to the definition limit, according to the diffraction limit, the spot diameter 2W0 at the focus length of an, at the focus of a lens is approximately proportional to which set of parameters? Will you please answer this? 2W naught to what is focus? It's proportional. D, you're correct. So this spot diameter, which is mentioned as 2W0, is directly proportional to lambda f divided by d. So how it comes, this equation, the fiber, suppose consider this is the fiber, this is the core. Here it is having the focus, focal focus light is coming. This is the lens. Let me draw the lens properly. This is the lens. This is the wave, and planar wave is coming and it's focusing here. So the D is the diameter of this, and the F is the focal length of the lens. And if you know the wavelength, if you know the F, if you know the D, you can easily uh, understand what should be the spot diameter, this spot diameter, and this will be exactly 4 lambda F divided by D. So you can achieve using this easily. Okay, so this is how it can be. Spot diameter can be uh, calculated. Next question is, why does the semiconductor industry use ultraviolet light or X-ray light for lithography instead of visible light? Option A, ultraviolet photons are slower, allowing more time for the chemical reaction on the chip. B, visible light carries too much momentum and would physically push the atom out of place. Then option C, shorter wavelength results in a smaller diffraction limit spot size, allowing for a finer circuit features. Option D, higher wavelengths increase the V number of the silicon, making it multi-moded. Option C. So, yeah, the shorter the wavelength results in the smaller diffraction limited spot. As we discussed about the spot size, it can be reduced because the lambda is proportional. So, lambda, if you're uh, shorter the wavelength, smaller the. We discussed in previous question that 2 omega naught. is proportional to lambda. So if lambda is decreasing, 2 W naught will also decrease. So this is the thing. Shorter the wavelength, shorter the spot size. And that's why we are using UV light, ultraviolet light, and uh, X-ray. EUV, we are saying EUV and X-ray. What was Einstein's key contribution to the photon picture in 1905 regarding the photoelectric effect? Option A, he derived the Maxwell equation from magnetic displacement current. Option B, he proved that light only travels in straight line as rays. Option C, he showed that photons have a rest mass equation to h by lambda c. Option D, he proposed that light itself consists of discrete energy packet called photon, where A is equal to h. Could you answer this? Let's try to answer. Okay, option D, you're correct because we already discussed about this one, and it's a very fundamental question. So he proposed that light itself consists of discrete energy packet called photons, and where E energy of the photon is proportional to the frequency and Planck's constant. Okay, so next question. How is the probability of finding a photon at a specific local location related to classical electromagnetic theory? Already we discussed about this one. Would you answer this? Option C. Yeah, you are correct. So the probability, we already discussed that PR probability in the area is uh, proportional to the intensity in that area. Okay, so this is like a proportional to the classical intensity of the light. So this is the probability of the finding photons. Photons are quantum particle, and the intensity, which is a classical phenomenon, classical behavior, is the gating probability of the photons in in that area depends on the intensity. So in the Gaussian beam, we discussed already. If you have Gaussian beam here, so finding probability of photons here is much higher here compared to this area. Given the energy of a photon in electron volt, EeV, what is the approximate formula to find its wavelength in micrometer? Could you answer this question? How to calculate the lambda? Option. Option B, correct. Why option B? Because A is equal to hc by lambda and E in electron volt if you consider, or lambda if you keep here. hc if you are comparing, then it will become 1.24. So lambda is approximately, you can say, 1.24. This is an electron volt. As we know the Planck constant in joule per second, so electron volt we can calculate. Mm, We can also convert it into joule also. Microjoule, millijoule, nanojoule. Energy can be calculated there. So, uh, so lambda can be calculated using this equation. Next question. What does the Heisenberg uncertainty principle for photons del E del T is greater than h cut 2 imply about a perfectly monochromatic light source? The photon must be traveling at the speed less than c to be measured. Option B, if the frequency uncertainty is zero, del E is equal to zero, the source must exist for an infinite amount of time. Del T is infinite. And then option C, the momentum of photon becomes zero when the time is known exactly. Option D, it means the photon can be in two places at once if the energy is high. What's your answer for this? Option B. So the option B is the correct answer here because we already discussed that monochromatic light source has the frequency uncertainty approximately zero. It will be monochromatic. And then the del T becomes infinite. Observation time becomes infinite or tends to become infinite. So this is how the option B is correct. Which of the following describes the momentum p of the photon? Could you answer this one? Option D. So it means that you're understanding the concept. P is equal to h by lambda, and you know that the k is equal to what? You know that actually this can be derived like this, but P by C, which is which can be further reduced like h by lambda, which can be further kept like this, h cut by k. Okay, so this is the correct answer. Now the question, what happens to the appearance of the black body source like a filament as its temperature increases? The emission becomes strictly monochromatic at the green wavelength. The light turns redder because the the photons lose energy to heat. Option C. The peak emission shifts towards the shorter wavelength, blue and UV, and the total energy increases. Option D. Photons starts to exhibit only particle property and lose their wave nature. Could you please answer this? Uh, Explain the sixth problem in the assignment. Which assignment? Week 3 assignment or week 2 assignment? Week 3. Actually, the deadline is still there. You need to. I can just explain you what is that. Let me complete this. Yeah. Let's finish this question and after that we need to watch that. Could you answer this one? Okay, Manuel, I'll check the assignment. This is, I think, very okay. Question 6, you're saying, not question 5. Question 5, consider the coefficient of weakly guide. Let me see the answer for what you said. Option number C. Yeah, you are correct. The peak emission shifts towards the shorter wavelength, low UV, and the total energy also increases because of the black body radiation. So, this. Okay, the correct answer is this one. Now, the question that you asked, let me share here. I don't know whether I can share or not. This one? Yeah. So there is mention core with refractive index, leading refractive index, single mode fiber. If the normalized propagation constant of the fundamental mode propagating inside the fiber is 0.85. Okay, the effective index is given. Experienced by the mode would be. Okay, so this is I think this is a just equation-based question. Let me see the equation for this. The equation is just simple as P propagation constant is equal to N effective minus N uh, Z divided by N1 minus N2. Did you try this to solve with this way? I think no, no, this is N2. Here B is the propagation constant and effective is given. Experienced by the mode would be. mm, Yeah, you can. I think you can solve it this way. Can you try this and check? Is it coming or not for you? The answer. It's mentioned, fundamental mode, means single mode. All these things are mentioned. So it can be easily, you just need to effective, yeah, I think effective index they are asking. Understood what to keep, what not to keep. They have given the normal propagation constant 0.85. They have given the single mode. Then you just N1, N2 also they have given. Just need to calculate the N effective. Anything else? Okay, so we were there. Let me see. I don't know how many questions are left. Yeah, there are a number of questions left. So we'll not do that much. We'll do two, three question more. So what about this one, this question? Which parameter describes the spatial extent of the fundamental mode in an optical fiber which may extend slightly into the cladding? Relay range and mode field diameter, cutoff wavelength, numerical aperture. Option B. Okay. So this is a mode field fiber. You're saying hmm, diameter describes the spatial extent of the fundamental mode in an optical fiber, which may extend slightly into the cladding. Yeah, you're correct. So this is the correct answer. Yeah. Now, next question. What I think this one we already did, I think. So, what about this one? For the Gaussian beam, how is the spot radius W naught is the focus related to the divergence angle theta c in the far field? Spot radius, how we get calculated in far field? This is important. Okay, so the correct answer here is option C. Why? Because the fundamental relation shows that spot as the far field, the spot size at the focus results in the larger divergence as the beam propagates away. So we don't need to consider the sine theta or something. We just can keep theta value, theta naught directly, lambda by phi theta. This is the correct answer. Okay, so fine. I think today's um, lecture will end here because there was n number of questions we have solved already. So uh, some questions will solve next week with a week 4 session where we will also discuss more about the electromagnetic wave nature and the quantum optics nature of the light. So we'll end the session here. Thank you for joining. If you have any doubts, you can ask me. I'll be here for a few more minutes, 10 minutes more. Yeah, you're welcome to join. Any help you want, any doubts, you can ask me.